Welcome to this video on methods for calibration of online moisture sensors. This is an online training video from the biofuels project, and I'm Henrik Kjeldsen, Senior Project Manager at Danish Technological Institute. The subject of this video is water or moisture in solid biomass. And the photo here shows an example of solid biomass. It's wood chips in front of a combined heating power plant. So the wood chips are going to be burnt in this power plant and produce heating and also electricity. Solid biofuels, as wood chips, contain dry matter, so that's organic compound, and these are the compounds that can burn in the boilers. But they also contain a lot of water, and the water mass fraction can be as high as 60%. Of course, the water don't burn, and therefore it's very important to know how much water there is in your solid biofuel. This is important, for example, when you trade biofuels. You don't want to pay for the water, only for the dry matter. There are two main techniques. One is the traditional loss and drying, where the water mass loss is measured in the oven. The problem with this technique, it takes time and you don't get the result immediately. You have to put effort into the measurements, and also you have to do sampling, and usually the amount of sampling and the limited amount of measurement result in a large uncertainty. So the more modern approach is to use some kind of moisture measurement device, as a microwave system shown in the picture to the right, which measures on all the sample passing below this conveyor belt. But in order to make this an option, we need to calibrate the device so they know what the reading of the instrument means, and this is the purpose of this video. The example we're going to look at is a microwave system. This is shown here, with some test sample material below. We want to make traceable water mass fraction measurements. So let's just remind that methodological traceability is a property of a measurement result whereby the result can be related to a reference through a documented unbroken chain of calibration, each contributing to the measurement uncertainty. If we look first at the SI definition, the SI definition of water content, that's typical water mass fraction. That's the one we use here. So that's the mass of the water divided by the mass of the original sample. It's easy to measure the mass of the sample, but the water mass is more difficult because you need some methods that's specific to water. Example of this could be the colorimetric Fischer titration or evolved water vapor method, and it's the second one we're going to use in this method. Loss and drying is not a traceable method because you don't know whether you can really whether all the weight loss is coming from water loss, or maybe there's some organic volatile compounds that's also evaporating. That said, loss and drying usually gives quite good results on biofuels. So we need a reference method, and as I said, we use the evolved water vapor method. It's somewhat similar to the loss and drying, except that the drying takes place in a closed chamber, and we measure the water content coming out of the drying gas with a sensor specific to water. So the measurement is specific to water, that's the crucial thing. Transfer standard, I'm not going to talk a lot about that, but I will mention that in the project, several transfers standard has been developed, as the one shown in the picture here. In industry, it could be many different kind of devices. One option, the one we are going to look most at here, is a microwave system, but it could as well be an infrared, a near system, or maybe a moisture transducer here. Now, to compare the result of different methods, we need some test sample material, and that's actually a critical part of the calibration process. The one we have proposed here is to take some white wood chips, so it's quite clean wood chips with no bark and few impurities. It's fairly small wood chips, so it makes them packing and stacking easier, handling easier. It's a mixture that's relevant for what is usually burnt at the power plant in question, so Norwegian spruce and Sitka spruce. And then there's another thing. When you do a calibration, this sample material must cover the entire measurement range that you're interested in. And we want to measure from 10% to 60%, so we have produced wood chips from 10 to 60% water content. You don't just go out and find this, that could be quite hard. So instead, the procedure has been to pre-dry the samples at 40 degrees to about 10% water, and then re-humidify the samples to the relevant fraction by adding water. This was done about 2 weeks before the measurement. The water was absorbed by the sample material, and the sample was thoroughly mixed before the measurements took place. This picture shows part of the calibration project. It has 2 other pictures. So the conveyor belt was stopped for the measurement, and there was placed a very homogeneous layer of wood chips of a known height where the measurement device was. And it's important to be very careful in this place, that do the measurement properly and handle the chips properly. Then, not shown in the picture, right after the measurement, fractions were put into sealed bags, sealed aluminium bags, to use them for reference measurements. And it's important that the sample material don't just lie around, that it's sealed very quickly so that it does not exchange water with the surroundings. The reference measurement on these bagged fractions of the sample material was made, as said previously, by the water vapor method, DTI. In addition to the reference measurement, there was also homogeneity measurement. They were done by taking several fractions before the reference measurements. And there were stability measurements, which was made by comparing subsamples for each fraction, taken before and after all the other measurements. One thing to be aware of is that there will be biological activity in wood chips when there's a lot of water, and therefore the water content will change of a sample lying around. This can be reduced by keeping the samples cooled. The uncertainty here, I'm not going through a full uncertainty budget, but just mention there are many contributions, regressions, so that that the fit of the instrument to the moisture, what's the standard deviation of that. There's uncertainty on the reference measurement, there's uncertainty of homogeneity, there's uncertainty of stability, and there could be other, like amount of impurities and what else it's relevant to measure. Here's an example of the measurement result. The way they are presented is we have the measured moisture on the horizontal axis and the reference value of the moisture on the vertical axis, and then there's a linear regression, and the scatter of the points around this blue line tells you the standard deviation of the reference method. In this case, the standard uncertainty for combined phase and attenuation result was about 1.5%, which gives an expanded uncertainty at just about 3%. So that's the total uncertainty and the result of this example of calibration. Thank you very much for your attention.